Hello students, welcome back. We're going to continue today where we left off. We're going to start with signal transduction part 9. Before we continue with our alpha 1 adrenergic receptor and its signal transduction, let's go back to the previous lecture just to review the alpha 2. Yes, we did alpha 2 last time. Now we're going to come back to alpha 2 at some other point, but I do want to go through this with you. Okay, we start out with our alpha 2 adrenergic receptor here. This is our alpha 2 adrenergic receptor. Now the first thing that's going to happen here is we're going to bring in our ligand. So norepinephrine is going to come in and bind to the alpha 2. Well, first, let's go back. Let's put everything back in the 0 position first. So we're going to have this here, and okay, let's get everything back to the 0 position. This here, potassium. Why can't I grab potassium? There it is. Oh, potassium is not by itself now. This always takes us forever. I hate this. I apologize for this, you all. Okay. I thought I had everything ready for us. Okay, potassium is inside. Okay. And now the last thing is that the channel here should not be phosphorylated. Okay, that's the top, and the phosphates. Okay, there are no phosphates there. Okay, and the receptor needs to be off. Okay, here we go. Now, this is the 0 position, except for this G protein. Wrong G protein. Okay, this is what things look like before. And so we have our alpha 2 adrenergic receptor, and we have our potassium is inside the cell, and our ion, whatever ion it is going to be outside the cell. So the first thing that has to happen is that the ligand, norepinephrine or epinephrine, binds to the alpha 2 adrenergic receptor. The alpha 2 adrenergic receptor, is it an inhibitory receptor or a stimulatory receptor? It's inhibitory. And so what's going to happen once that binds, once the ligand binds to the alpha 2 adrenergic receptor, that's going to activate the receptor. So now the alpha 2 adrenergic receptor is going to be activated. And so now when it becomes activated, now the G protein is going to now move. The G protein is going to move to the receptor, the activated receptor. Okay. Now I'm going to ask you all, so the this is G protein, G inhibitory protein, alpha, beta, gamma with GDP. What's going to be the next step in this process? Nope. Beta and gamma don't break away yet. You have to change GDP for GTP first. So that happens first. And so the first thing that's going to happen, you're going to get the G. Okay. And so the next thing that's going to happen is the GDP is going to go away. And you're going to have GTP. That's the first thing. Now what's going to happen? Okay. Okay, you can say alpha breaks away or beta gamma breaks away. So let's move beta gamma moves out of the way. Now what's going to happen? Exactly. Alpha inhibitory GTP, which is the active form, is going to go where? It's going to go to adenylyl cyclase. Okay? And what is that going to do to adenylyl cyclase? It's going to activate adenylyl cyclase. It's going to inhibit adenylyl cyclase. So you're going to get no conversion of cyclic AMP, no protein kinase A activation. no phosphorylation of this ion channel, and so this ion channel is going to remain closed. Make sense? What's going to happen to beta and gamma? The beta and gamma are going to go to the potassium. This potassium channel, what are they going to do to that? What are they going to do to that channel? They're going to open that channel. So they're going to activate that channel. So the channel was the potassium channel. Well, I don't know why I don't have it there. Oh, yes. The potassium channel, there it is. It was closed. Now the potassium channel is going to open up, and then the potassium is going to leave. And so basically what we've done here is have we made this cell more positive or more negative with these two things? More negative. And negativeness turns the cell off. And so this cell is now going to be turned off. You don't know how it's going to work yet because I just made it a very generic cell. But later on we'll look at exactly what it does physiologically. Just want you to see the biochemistry first. So this is how alpha-2 adrenergic receptor, which is an inhibitory receptor, turns a cell off. It makes the cell more negative. It hyperpolarizes the cell. Make sense? So now today, we're going to move to alpha-1. Now let's go to the alpha-1 adrenergic receptor. And I'm going to actually tell you where alpha-1 works. Because, well, I told you where alpha-2 works, at presynaptic nerve endings. But we're going to look at presynaptic nerve endings in a lot of detail later. Okay? So let's go to the alpha-1 adrenergic receptor. Okay, so let's get rid of this. Okay. So let's make ourselves a membrane here. Okay, we're going to make ourselves a membrane. And now we're going to put a receptor in that membrane. Okay, which receptor do we want to put in this membrane? Okay, I'm going to label things as I go. That's going to take a while. So there's the membrane. Now we're going to put our receptor in the membrane. Which receptor are we going to look at now? Alpha-1. So let's here draw ourselves an alpha-1 adrenergic receptor. 1, 2, 3, 4, 5, 6, 7. Actually, I don't like that color because I need to use red for something else. 1, 2, 3, 4, 5, 6, 7. Okay. So this is our alpha-1 adrenergic receptor. Okay. So I'm going to label this here. Alpha-1 adrenergic receptor. Okay. Now we're going to need a ligand. We're going to need some sort of agonist or ligand to bind to the alpha-1 adrenergic receptor. What ligand could we use? Norepinephrine. Exactly. So you all are remembering this very well. Norepi. Okay. So norepinephrine is going to... Now, alpha-1, let's go back. Alpha-1 adrenergic receptor. Is it an inhibitory receptor or a stimulatory receptor? It's a stimulatory receptor. So should it turn this cell on or turn this cell off? It should turn this cell on, exactly. Very good, very good. Now, this receptor then, if you think about it, should it put ions into the cytosol or take excuse me, should this cell become more positive or more negative? More positive, exactly. So should it put ions, cations, into the cytosol or take them out? Should you put them in? Does that concept, that's a real basic general concept that you need to understand. Exactly. So that's what we're going to be trying to do here. We're going to turn this cell on. But this is a smooth muscle. So this is going to be a smooth muscle. So do we want this smooth muscle to contract or relax? This is a smooth muscle. I've got different answers. I need the same answer. This is a smooth muscle. Do you want this smooth muscle to contract or relax? Still getting different answers. Okay, think about it this way. Let's see. Alpha 1. We have alpha 1 adrenergic receptors in the blood vessels. In the blood vessels going to our stomach. In the blood vessels going to our stomach. We have alpha 1 adrenergic receptors. Okay? Now, and so around that blood vessel, you have the smooth muscle. You have smooth muscle there. Now, when a dog is chasing you, do you want to put more blood to the stomach or less blood to the stomach? Less blood to the stomach. You want to put less blood to the stomach. Okay? So, if you want to put... Did I say that right? Yes, yes. If you want less blood to the stomach. So during, let's say, hold on, what have I done? What am I doing? I'm doing alpha 1. Alpha 1 is stimulatory. Alpha 1 is stimulatory. The two stimulatories are alpha 1 and beta 1. And it's always alpha 1. So for alpha 1, if it's stimulatory, now, so during a sympathetic response, do you need for that blood vessel to contract or relax? You need it to contract. You need it to contract, exactly. Yes, constrict. Yeah, you need the muscle to contract so that the blood vessel will constrict. Exactly. And so when you have an alpha 1 response, you need to stimulate that muscle. You need to turn it on. You need contraction. Make sense? So that's what we're going to be trying to do here. We're going to try to get this alpha 1 adrenergic receptor to turn the smooth muscle on, to make the smooth muscle contract. Okay? Is everyone clear about that? Because if the biochemistry doesn't match the physiology, it's pointless. Okay? And so, here we have our norepinephrine is going to bind to our alpha 1 adrenergic receptor. And so we should end up with, I'm going to put here, we're going to end up with contraction. This is the last step here, but I'm just going to go ahead and put it here because this is what we want to get to, contraction. Okay, that's what we're trying to get to. But there are lots of steps in between the binding and the contraction. And what we're going to figure out today is, what are those steps? What are those signal transduction events? Make sense? Okay, let us continue. So, when norepinephrine binds to the receptor, what's the first thing that's going to happen here? You're going to activate this receptor. So this receptor is going to become active. So now this receptor is on. What's the what family of receptors is this? What's a name for receptors that have this shape? 7-pass transmembrane receptors. What else? Serpentine receptors. That's another name. The coupled one. What is coupled to it? G protein coupled. It's G protein coupled. And so we have our G protein coupled receptor. So if we have a G protein coupled receptor, we need to add something to it. We need to add a G protein. So in the cytosol here, we're going to have a G protein. And this G protein is going to have 3 units on it. Okay, now you all won't know this one, but we'll get it. It's going to have alpha. And alpha is going to be attached to GDP starting out. And then we're going to have beta and gamma. Now we've looked at 2 different G proteins so far. We looked at what are the 2 G proteins we've looked at so far we've seen in the past? We looked at G. Exactly. Put this on its own layer. That's going to confuse us later. We've looked at G stimulatory and we've looked at G inhibitory. Now, which one is this going to be? Is this going to be a G inhibitory or a G stimulatory? Since it stimulates, it should be a G stimulatory, but it's not. Because if it were a G stimulatory, it would work by one of the same mechanisms we've seen so far, and it doesn't. And it's not G inhibitory. It's a brand new G protein. Wow, that's a lot of fun. Okay, this is going to be called GQ. GQ. You know, like the magazine, GQ. Okay, so we're going to have a beta Q, a gamma Q, and an alpha Q. I'm going to make this one another color. GQ is always associated with alpha 1. Always. Beta 2 is always associated with what? G stimulatory. And alpha 2 is always associated with G inhibitory. Okay? Now, that's what we're ready to get into. I'm going to show it's the signal transduction events that follow this. You don't know anything about these yet. This is going to be something completely new. Okay? Okay. So let's go back to our beginning. So what's going to happen? Norepinephrine is going to bind, turn this receptor on. Now, just like before, this whole G protein, this entire G protein is going to then move to the receptor. What's going to happen next once the G protein gets to the receptor? Exactly. You're going to remove GDP and put in GTP. So I'm going to just put here beta gamma so I know that. Okay. So let's do that now. Let's zoom in here. Okay. Okay. And now let's change GDP to what? What are we going to change it to? GTP. Everything looks pretty similar so far. Nothing has changed. So what's going to happen next? Figure out what's going to happen next. Beta and gamma are going to move away. Beta and gamma move away. Now what's going to happen? So this here, the alpha Q GTP is going to go and activate adenylyl cyclase. And that does not happen this time. We're going to have a new protein, a brand new protein. Okay? And this protein, what this protein is going to do, right in the membrane of the cell, I'm going to put this in the membrane of a cell. You have these, let's just put some going this way. Oops, I don't want to make that. That's going to be a mistake. In the membrane of a cell, you have these things that have this shape, look like lollipops. Some of them are turned this way, and some of them are turned this way. Does anybody know what these structures are called in the membrane? Phospholipids. Exactly. Exactly. One of those phospholipids in the membrane, one of them is called phosphatidylinositol bisphosphate, PIP2. I will. So this is going to be, I'll abbreviate it first. It's PIP2. Let's just keep it there for now. Let's just keep it there. The phospholipid is PIP2. Now, what's going to happen in the membrane? Within the membrane, there is a protein. And what this protein is going to do, I'm going to put the protein right here. This protein, let's make this protein really happy. What this protein is going to do, it's going to phospholipids. Well, I'm going to give you a really rough drawing of this, of PIP2, one PIP2. I want to put it on. How am I going to do this? Well, I'm not even going to worry about that right now. You're going to cut that phospholipid. You're going to cut off those fatty acid tails. And so if this is PIP2, that means it has 3 phosphates associated with it. I'm just going to put one of the phospholipids here so you can see. Phosphate, phosphate, phosphate. That's PIP2. Phosphatidylinositol bisphosphate. So it has 3 phosphates on it. PIP2. And so what's going to happen? This enzyme, or this protein, is going to catalyze the conversion. Is what it's going to do. It's going to clip this. It's going to make 2 parts. One part is going to have the fatty acid tails with the glycerol, and the other part is going to have the round part with the 3 phosphates. You should be able to just look at that and see if it cuts out a certain way. You're going to have the 2 sticks of the lollipop and the candy of the lollipop. Can you see that? Okay. You see this molecule here, PIP2. What's going to happen? This protein is going to cut this lipid right here. It's going to cut it across there, right there. And so you're going to end up with the 2 lollipop tails together. I mean the 2 sticks of the lollipop right here. And then you're going to end up with the round part, the polar head group, with the 3 phosphates on. You're right. That's after after alpha Q activates this protein. We're not going to give you any names right now. I just want you to know what takes place first, and then we'll name them later. So everybody okay with where we are now? Okay. Now, both of these, the sticks and the candy, are going to both do something. Okay, let's first let's do the candy first. Let's do the candy first. Okay, and let's see what we have here. Okay, I want to put the candy by itself. Okay, so what the candy is going to do, it is going to activate in this cell. We're going to have a membrane here. And this membrane in the cell is going to store lots of calcium. And what's going to happen, this candy is going to go down and it's going to activate this membrane, and this membrane is going to release its calcium. And this calcium is going to come out. Look familiar? Exactly. That calcium is going to come out. And now what's going to happen, that calcium is going to activate, it's going to go and activate another protein. It's called a calcium modulating protein. It's going to activate a calcium modulating protein. And I'm going to go ahead and give you that name, the name of that protein here. That protein is called calmodulin. 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 And so this calcium is going to come out of those vesicles, activate a protein called calmodulin. This calmodulin is then going to activate yet another protein. It's kind of a long one here. It's taking us a while to get to this one. It's going to activate another protein. This protein is going to be called CAM kinase. CAM kinase. Calcium modulated kinase. So the calmodulin is going to go and activate CAM kinase. What do kinases do? Do y'all remember what kinases do? They add phosphates. Very good. Very good. So we're almost getting there now. Okay. Now I'm going to go straight to the last step here. In smooth muscles, okay, you're going to have myosin here. And then you're going to have the light chain of myosin. Okay. And what do those, let me make this one real light here. You all remember what those myosins bind to? Actin, exactly. But now, in smooth muscle, you don't have troponin and tropomyosin. All you need to do now is add a phosphate. Once you phosphorylate those light chains, it activates them, and now they cause the cell to constrict. They cause those muscles to contract. So all we need to do is add a phosphate to this. So what could we use to add that phosphate? Which kinase? CAM kinase. But that's not, it's one more step though. There's only one more step, but you're all on the right track. CAM kinase actually phosphorylates and activates one more kinase. And this kinase is going to be called myosin light chain, because there's a light chain. Myosin light chain LC kinase. And now myosin light chain kinase is going to go over myosin light chain kinase is now going to go over and add a phosphate here. And now when you add a phosphate to the light chain, now that activates it and you get contraction. And that's what causes the smooth muscle to close up. And that's how alpha-1 adrenergic receptors stop blood or prevent blood from going to your stomach or your kidneys when you don't need it. Kind of makes sense? This step, there are a lot more steps in this one because we have a lot of kinases involved. Whereas in the heart, you don't really, all you have to do is let the calcium go. It binds to the troponin, and things are okay. Oh yes, the CAM kinase adds a phosphate to myosin light chain kinase. Now this is in blood vessels. This is in blood vessels. There's a little, the situation is going to be a slightly different, just slightly different when we start looking at, later on. Okay. So now we know what the candy part of the lollipop does, but we don't know what the sticks do. What do these sticks do? And we'll look at that in just a second. So let's just go through the whole process quickly. Norepinephrine binds to the alpha-2 adrenergic receptor, turns this receptor on. That releases alpha-Q-GTP. Alpha-Q-GTP binds to a protein here. This protein clips one of the phospholipids to make the 2,6 and the head group. The head group goes to this vesicle here, releases calcium. The calcium activates calmodulin. The calmodulin activates CAM kinase. The CAM kinase phosphorylates myosin light chain kinase. It's now active, and the myosin light chain kinase phosphorylates the light chain, activates it, and you get contraction. Let's name them all now. Before we tell what the sticks do, let's just name everybody. Okay? Now, since we are cleaving, I'm going to put all the names on one layer here. That's going to make it easier. Since we're cleaving a phospholipid here, this protein is called a phospholipase. Phospholipase C. Phospholipase C. That's this protein. Phospholipase C. Lipase C. Okay, let's go ahead and name. We'll tell what the sticks do tomorrow, but we'll name them now. Okay. What is the name of the 3-carbon compound in lipids and phospholipids? Glycerol. And so this compound has 2 acyl groups on it, or 2 fatty acids, or 2 fatty acyl groups. So we call this compound diacyl glycerol. DAG. And that's diacyl glycerol. Now this head group here is a compound called inositol. That's why it was phosphatidylinositol biphosphate. And so this head group is now called IP3, inositol triphosphate. But that's all I need you to know. Just know IP3 for now. This membrane here that holds our calcium store is just the ER, the endoplasmic reticulum. Now we've already named all of these other proteins. So I think we have everything here. So we see how that's what we're going to stop this. I'm not even going to tell you what DAG does because it's not really involved that much in contraction. Okay, if you all would, let's see how much you remember. Close your notes. I have a few questions for you. The alpha-1 adrenergic receptor, is it inhibitory or stimulatory? Stimulatory. So is it going to cause muscle contraction or muscle relaxation? Muscle contraction. What is the G protein associated with the alpha-1? GQ. What protein does GQ activate? Phospholipase C. Phospholipase C. And phospholipase C clips PIP2 to create two things, the sticks and the head group. What are the sticks called? DAG, exactly. What is the head group called that's clipped up? IP3. IP3 releases calcium from where? The endoplasmic reticulum. Okay. The calcium from the endoplasmic reticulum activates a protein. What's the name of that protein? Calmodulin. Calmodulin. Calmodulin activates another protein. What's CAM kinase? What is the job of CAM kinase? Phosphorylation. What protein does it phosphorylate? Myosin light chain kinase. And what does myosin light chain kinase phosphorylate? What does myosin light chain kinase phosphorylate? What light chain? Myosin light chain. And when myosin light chain kinase is phosphorylated, what happens? Contraction. Have a great day, you all.